Thank you very much, Ben. I hope you all enjoyed that. We can do a little Q&A. If anyone has any questions, just pop your hands up and me and my colleague Caroline will run around with the mics for you. Why is there a hand shot up at the back?
Right at the top.
Who else we got?
There we go.
Run up for me. Is there anyone nearer me? No?
I do hope it's left you with more questions than answers. That was the idea of the talk.
What stage is the sun at the moment?
So currently our sun is in its main sequence. So what our sun is doing is our sun is turning protons and neutrons, well, it turns protons into helium. And to do that, it requires that weak force to transform protons to neutrons. And so it's doing this right now. It's forming helium. And when it does that, it releases the light. And so the reason the star shines is because this is happening right in the center of the sun.
Why is the element technetium grayed out?
Great question, always asked. So technetium is grayed out. So technetium is element 43. And the reason it's grayed out is because, for the same reason promethium is grayed out, is that there aren't any long-lasting isotopes. I won't say stable because, of course, uranium doesn't have a stable isotope either, but there aren't any long-lasting isotopes. And by isotope, I mean versions of that atom. And so essentially, if you had some technetium, it would decay pretty quickly. And so we don't find it in nature. And so technetium and promethium here, they had to be created in particle accelerators. Actually, promethium was found in the kind of decay of, in the fallout of an atomic bomb. And so these guys only exist for short periods of time, so we wouldn't find them in nature naturally.
There's no boson for gravity. Do you think the hypothetical graviton exists?
A hypothetical graviton definitely exists. Yeah. An actual graviton, we're not sure. I mean, if we extend the field theories that we have, and the idea, for instance, that the Higgs boson existed, came from the idea that we needed the Higgs field to give mass to particles. Then if essentially we can have a kind of gravitational field theory in the same sense that we have the quantized field theories for the other interactions, then I think that, yeah, it may well exist. Actually detecting a graviton would be nigh on impossible. When the neutrino was first predicted, essentially Wolfgang Pauli, who predicted it, was a little bit dismayed because he said that he'd predicted something that could never actually be proven. So as a theorist at the time, that was horrendous for him. It took 26 years, but the neutrino was discovered. The graviton would be thousands of times more difficult than the neutrino to detect. And so it's as to whether we get an experimental method or technique that we can use to be that sensitive to detect these things. So, but a hypothetical one definitely exists. Yeah.
What is helium-4?
What is helium-4? So, on the periodic table, you'll notice that helium is the second element on the periodic table, but helium contains 2 protons and 2 neutrons. So the 4 stands for how many protons and neutrons it's made from, which is something also called its mass number. So you can get other forms of helium. So helium is a particle, well, helium is helium because it has 2 protons. But if I take away a neutron from it, then this is still a form of helium, but this is called helium-3. It's got 2 protons and 1 neutron, so 3 protons and neutrons in total. But helium-3 doesn't like to exist, really. It's not very stable. And that's why it's much happier if it connects with a 4th particle, another neutron, to form helium-4. Yeah.
Why didn't you put elements 93 to 118 on the periodic table over there?
Good question. It was for the same reason that technetium and promethium were grayed out. So they are very unstable, and so they don't occur naturally. And so I only put up to uranium because they are essentially the only naturally occurring elements that we see. Fantastic question, though. Thank you.
Does anyone want to go to the Rutland Astronomical Society?
Yes. Thank you. There's a coach outside. Yeah.
So, what are the other stages until we got to iron?
Until we got to iron. Great question. So, what happened was those helium nuclei were continually placed upon the stack until we built the stack up so high that we reached something called nickel 56. And then what happened was there was a beta decay, and that turned into iron. And so it was lots and lots of these helium being stacked on top of one another until we got the stack so tall that we created something which was really solid. And if you added something else to it, that would make it less solid and less stable. And so it was the same process that created carbon and then oxygen that continued to stack on to form iron 56. Does that help? Yeah? Cool.
What's the particle reaction once a star goes supernova in the making of a black hole?
Oh, okay. So, well, in the supernova, in the collapse, these nuclei kind of get squished in with lots and lots of protons and neutrons. And what happens is those neutrons actually get absorbed by the nucleus. So they rapidly gain weight by sticking protons onto them. And then those protons will later on decay into... So those neutrons that have been added on will later decay into protons to form those other elements. The creation of a black hole is due to such a vast force of gravity that the crushing of the matter is so intense that you can't basically have a form of matter that feels that greater force. So in between the death of, say, our sun and a black hole, we will actually form something called a neutron star. And so as the particles are falling in, what happens is, in the same way that electrons build up inside of an atom to higher energy levels, all of these particles start stacking to higher energy levels. And they form a pressure which pushes back against the infalling matter. First of all, the electrons push back, and that's what's going to happen when our sun dies. It's going to form something called a white dwarf. And that white dwarf will be formed because the electrons are pushing back with enough force to stop the rest of it all collapsing inwards. But the electrons are only so strong. And if the mass is greater, they will collapse inwards. And the next building blocks that are available to actually hold up the star are neutrons. So what happens is all of the electrons and protons merge to form neutrons, and they stack up until the neutrons are pushing back with a force to try and stop the infalling matter. But the neutrons are really the end game, because the neutrons are the strongest particles that are able to actually stack to push back. And if the neutrons can't hold back the infalling matter, then everything gets crushed so much that space and time itself rips. And that's what a black hole is. It's essentially a sink and a tear in space and time where it's not really a form of matter, but it is nothing but like a plug hole where matter gets sinked into.
With how various atoms advance through forming, adding a helium each time, why does it add a helium and not two slightly larger atoms?
Great question. So remember I mentioned that these particles have charges, electric charges. So the helium atom with 2 protons has a positive 2 charge. Okay? If we think about the carbon nucleus, it's got 6 protons, so it has a positive 6 charge. The greater the charges, the greater the forces, because the charge represents how these particles interact with the force. And of course, they've both got positive charges, and so they want to actually repel each other. But because they've got so much energy, they can come together and collide and stick. But if you had particles with a greater charge, the force would be greater, and so you would need a greater amount of energy to bring them together to stick together. And so with just a 2+ charge, it's much easier to bring a helium towards a carbon than it would be to bring another carbon towards a carbon.
My second one, so with carbon, like, I know there's the triple alpha process with 3 helium atoms. What's the difference between that and the other process?
All right, so nicely spotted. So what I was showing was actually the triple alpha process. So this is actually the triple alpha process. But the reason I've put it like this is so that we can talk about the fact that beryllium-8 doesn't exist for a very long time, but it's essential to form beryllium-8 before then another helium crashes into it. But if you look, we've got 1 helium, 2 helium, 3 helium, and another word for a helium nucleus is an alpha particle, and that's why it's called the triple alpha process, the 3 heliums coming together to form carbon. See?
I'm not sure if this has kind of been answered, but how would you get hydrogen?
So hydrogen, being the simplest element, is really just a proton plus an electron. So a proton is essentially the nucleus of a hydrogen atom. So once an electron combines with the proton to form something electrically neutral, then that's an atom of hydrogen. Okay? And so hydrogen is the most abundant element in our universe still, because really it's just the most basic and simple, and there were lots of protons around from the Big Bang.
Going back to the black hole, as you said, how can you know what a black hole is if no one's ever really experienced one, because no one's ever survived one or properly known what one is?
Okay, this is going a little outside my area of expertise, but I'll give you my... So, very good question, and I guess the truth is that they are still in a very big way theoretical, but we have seen a lot of astronomical evidence which behave in a way that we would imagine that theoretical black hole to actually behave. So, for instance, such a concentration of mass, which causes such a large force of gravity, that stars at the center of our galaxy orbit around it. And there's nothing there that we can see, obviously. There's no glowing object, and so therefore we assume it's a black hole. The same when you may have seen the image which looks like Sauron's eye of what they've said is an image of a black hole. That is the matter from a star that's falling into the black hole and being accelerated as it falls in. And as it's accelerated, it's emitting light. And by looking at that light, we can tell how much it's being accelerated, and therefore how much gravity the thing in the middle must be imposing. And so therefore, there's lots of indirect evidence, but in a way, we can't get real direct evidence because there's no way of sending information out of a black hole. So the only way we can see them is indirectly like that. Does that help?
How was the Earth's atmosphere created?
The Earth's atmosphere, oh God, this is outside of my area of expertise. Well, I mean, there were a number of different stages, I believe. There was lots of outgassing when the molten Earth was cooling down, and volcanoes were being formed. There was lots of we started with a carbon dioxide-rich atmosphere, I believe, and then organisms developed that were able to use that carbon dioxide and sunlight to produce foods via photosynthesis. As they did that, a byproduct was oxygen, and then the oxygen obviously now forms over 20% of our atmosphere. So it's quite a complicated process forming the atmosphere, but as I say, that was the astrophysics bit. So I apologize if my answer isn't as detailed as you'd like.
At the very beginning, why is it helium that was formed rather than the hydrogen?
Well, as mentioned, the hydrogen is just a proton with an electron, and so the protons were the first particles to be formed. So if you like, the nucleus, the heart of hydrogen atom was actually formed in that first second. So you could say that the first element, hydrogen, was formed in that first second. It was just that to produce these helium, the central part of a helium nucleus, you essentially needed something else to take place. You needed those particles to slam into one another to stick. So yeah, I guess you can say then that hydrogen was created in the very first second after the Big Bang.
More exotic particles like muons and strange quarks, for example.
Energy. So energy is the key here, because if we think about it, the standard model, in fact, I know I've got one just after my final slide. The standard model, as I mentioned, kind of breaks down nature into its constituents. And we've got, there we go. And so we know we've got these first generation of particles, and really that's all you need to build what we have around us. But if you give extra energy when you're creating particles, you pump them up. And the way you pump them up is you pump them up in mass. And so you can create these heavier particles if you have more energy in collisions when you collide them together. So they can be created in particle accelerators, like the Large Hadron Collider at CERN, when they collide together and their energy forms massive new particles. Or in cosmic rays, where high energy particles are hitting the upper atmosphere and again producing these things. Muons, there's about 1 muon going through every second at the moment. From cosmic rays. So muons are around us all the time. And in fact, particle physicists use them to actually calibrate machines with, because they're well known and well understood. So these things do exist, and they do exist around us, but they only exist for fleeting moments. And eventually they will form these lighter first generation particles.
What do you think dark energy is? Because for me, I think it's like an anti-gravity, and black holes are where they're sort of fighting on the same ground and tearing apart space and time.
Good question. Again, dark energy, kind of out of my realm, but so for those of you, I'm sure you're all aware of dark energy. So we seem to be in a universe which is expanding, but expanding at an accelerating rate, which means that despite the fact that gravity should be pulling everything back towards each other, there is something driving the expansion and actually accelerating it outwards, which is a little worrying because we don't know what it is. So it's described as dark energy because the way in which we describe whether the universe is going to contract or expand is to do with the energy content in the universe. Right now, I'm not sure what dark energy is. I'm not sure whether it is an artifact of our model, so our scientific theory. Maybe we've got something wrong in our analogy of the universe at that scale, because we've only really just started looking out into the universe in that wider realm. So it might be that we don't actually have the right analogy to explain it. But I like your idea that it's anti-gravity, because as you've said, it is something which is acting against gravity, wanting to pull in. It's actually pushing out. So follow that lead, learn more about the analogy and find out where it breaks down, and you may well be right.
The heavier elements are built by adding heliums. Why aren't they built by adding individual protons?
Good question. So the reason is to do with the stability of those nuclei. So the way in which these particles build up is they fill energy levels. So electrons around a nucleus will fill energy levels because these particles can't all exist with the same properties. So they have to then stack on top of one another. And just in the same way that electrons stack into energy levels around a nucleus, protons and neutrons also stack into energy levels within the nucleus. And it just so happens that in the same way that we get chemically stable elements, the noble gases, we also get quite stable nuclei when we have full shells of protons and neutrons. So helium has a full shell of protons and a full shell of neutrons, something which is known as it being doubly magic. which means that it's more stable than the elements either side of it. So it's more stable than it should be, given its place in the periodic table. And so that means that if you add a proton, you create something which is less stable, and it doesn't want to be less stable, and so it will just go back to helium-4 again. And so really you're stuck in a rut, and the only way to get out of that rut is by jumping to carbon-12, and carbon-12 is more stable, and so it's happy to exist as carbon-12 and not fall back into being helium-4 again.
Sorry, I was just thinking about sticking quarks together again. So are you saying that an up quark can be red, green, or blue, and a down quark can be red, green, or blue? So there's 3 different kinds of each.
Absolutely, yeah. So the colours don't denote what type of quark it is, up or down. In my model, I tried to, so in the analogy I've used, I've tried to denote the up quarks as being on top of my models and my down quarks on the bottom of my models. But the color can be red, green, or blue. It doesn't matter. And that's simply because it only tells us about the strong interaction. And as long as we have one red, one green, and one blue, we can never tell which quark it is that has that particular color charge, because we can never see quarks standing alone. From that first fraction of a second after the Big Bang, they've always been bound into these particles. So we can never see a quark by itself to say, yep, that's green. And so we can't actually say whether up quarks are predominantly red, green, or blue, and so we therefore have to say that they are all red, green, and blue. Yeah.
Well, thank you so much for all of your questions. They were great. As I said before, Ben will be signing some books outside if you want to go chat to him and say hi. And all that's left is to say thank you again to Ben. Thank you.
Thank you.